You type Python tutorial into Google. In under 200 milliseconds, Google ranks results from 100 billion web pages. That's faster than a human blink. Think about what that means. The web has 1.9 billion websites. Content changes every second. A linear scan at 1 microsecond per page would take 28 hours per query. Google answers yours before your finger lifts off the keyboard. This isn't magic. It's a purpose-built distributed system that took 25 years to perfect. Here's exactly how it works. Let's anchor on the real scale. Google indexes over 100 billion web pages across 130 trillion discovered URLs. It processes 8.5 billion search queries per day. That's 98,000 queries per second sustained 24/7. Googlebot crawls 20 billion pages every single day. That's 2 petabytes of raw HTML downloaded daily. In 2000, Google's entire index fit on 10,000 hard drives and took 4 months to rebuild. Today, rebuilding from scratch is no longer feasible. Google runs a continuous crawl index serve pipeline just to stay current. Every number here is a design constraint, not a marketing stat. Before the solution, understand why obvious approaches collapse. AltaVista dominated search in 1997. It indexed 250 million pages using linear scans and simple keyword indexes. Results were spam-filled garbage because it had no relevance ranking. Google launched PageRank in 1998. AltaVista's traffic collapsed within 2 years despite having a larger index. 3 naive approaches all fail at Google's scale. Linear scan, 28 hours per query. Simple keyword hash map, no ranking, useless noise. Single server, even a perfect index needs 98,000 QPS. One server handles 10,000 to 50,000 QPS max. You need all 3 problems solved simultaneously. Now here's where it gets interesting. Googlebot is a distributed crawler running on thousands of machines. Think of it like a postal service that never stops delivering. The URL frontier is a massive priority queue, ordered by PageRank of linking pages, freshness requirements, and domain authority. The fetcher downloads raw HTML via HTTP, HTTPS, handles redirects, and checks robots.txt compliance. The parser extracts text, title tags, canonical URLs, and all outbound links. Discovered links feed back into the frontier. Googlebot crawls 20 billion pages per day, about 231,000 pages per second. A site receiving more than 5 Googlebot requests per second is seeing unusually heavy crawl traffic. But here's the catch. Googlebot can't recrawl 100 billion pages at the same frequency. It stratifies by importance. Tier 1, news sites, Wikipedia, major e-commerce, recrawled every few minutes to hours. Tier 2, active blogs, medium traffic sites, recrawled every days to weeks. Tier 3, low traffic pages, recrawled every weeks to months. Tier 4, near duplicate, orphaned pages may never be recrawled again. A crawl delay directive in robots.t limits fetches to 1 per n seconds. Last modified headers and sitemap lastmod tags signal when recrawling is worth it. This tiering is what makes 20 billion pages per day operationally possible. The inverted index is the engine underneath every search system. Forward index maps documents to words, useless for search. Inverted index maps words to documents. For the word search, you instantly know which documents contain it, at which positions, with what frequency, in which field. Position data enables phrase matching. Machine learning is not the same as learning machine. Field data boosts title matches over body matches. Google compresses posting lists using delta encoding, storing differences between consecutive document IDs instead of absolute values. A compressed posting list uses 10 to 50 bytes per entry versus 16 to 32 bytes uncompressed. That 2 to 3x reduction is critical at petabyte scale. This is why engineers lose sleep over encoding schemes. PageRank was patented in 1997, published by Brin and Page in 1998. The insight was simple and devastating to competitors. A link from page A to page B is a vote for B's authority. A vote from a high authority page counts more. Think of it like academic citations. A citation in Nature carries more weight than one in a blog post. The damping factor D equals 0.85, modeling a random web surfer who follows links 85% of the time and jumps to a random page 15% of the time. PageRank converges after 50 to 100 iterations across the full web graph. At 130 trillion URLs, one iteration processes 130 trillion edges. Google runs this on a MapReduce cluster. Modern Google uses 200 plus ranking signals, but PageRank remains foundational. Google built custom storage because off-the-shelf databases couldn't survive their scale. Bigtable, publicly documented in 2006, is a distributed wide-column store. It stores raw HTML with key equals URL hash and value equals raw HTML plus metadata plus crawl timestamp. Rows are sorted by key. Range scans over URL hash ranges are extremely efficient. Colossus, the successor to GFS, provides the distributed file system underneath, petabytes per cluster across tens of thousands of servers. Spanner handles URL deduplication and globally consistent metadata. It provides external consistency across data centers using true-time atomic clocks. Borg, Google's cluster scheduler predating Kubernetes, manages all compute across these layers. This is the infrastructure that Kubernetes was designed to replicate for everyone else. Building an inverted index from 100 billion crawled pages is a batch processing problem at petabyte scale. Google invented MapReduce in 2004, specifically to solve this. The map phase takes each document and emits a tuple per word: word, document ID, position, field, and term frequency. The shuffle phase groups all tuples by word across the entire cluster. This is the bottleneck. It requires moving petabytes of intermediate data across the network. The reduce phase consumes each word's grouped tuples and writes a compressed posting list. Google later replaced MapReduce with Cloud Dataflow, Apache Beam internally, for lower latency incremental index updates. Bing uses a similar pipeline on Azure HD Insight with Azure Blob Storage for the raw crawl corpus. Now here's where it gets interesting. A query enters Google's serving stack and must return ranked results in under 200 milliseconds. Step 1. Query understanding. BERT and MUM neural models handle spell correction, synonym expansion, entity recognition, and intent classification. Is this navigational, informational, or transactional? Step 2. Index lookup across thousands of sharded leaf servers in parallel. Each shard holds a slice of the full 100 billion document index. Step 3. The mixer aggregates partial results. Step 4. The global ranker applies 200+ signals: PageRank, Core Web Vitals, Freshness, EEAT scores. Final results returned to the user. The entire pipeline completes in under 200 milliseconds, every time, at 98,000 QPS. AltaVista and Google faced identical problems in 1998. AltaVista actually had a larger index, 250 million pages versus Google's initial crawl. But the architecture decisions diverged completely. AltaVista used linear scan augmented with keyword indexes and had no link-based ranking. Results were overrun by keyword-stuffed spam. Google built PageRank as the centerpiece, treating the web graph as a voting system. AltaVista's traffic collapsed within 2 years. This is the canonical case study for why data structure and algorithm choices at the system level determine product survival. Elasticsearch today uses inverted indexes with BM25 scoring. Same principle, different tuning. Algolia adds typo tolerance and faceting on top of the same inverted index core. Google isn't the only system worth studying here. Microsoft Bing indexes 10 to 20 billion pages using Azure Blob Storage for raw crawl data and Azure Cosmos DB for URL frontier management with multi-master global rights. Bing's crawler is called BingBot and respects the same robots.txt standard. Elasticsearch powers search at Uber, GitHub, and Wikipedia. It shards inverted indexes horizontally across nodes. A single Elasticsearch cluster at Uber handles billions of trip log documents. Algolia targets developer-facing search. It pre-computes ranking at index time instead of query time, achieving sub-10 meta responses by trading storage for latency. Each system makes different trade-offs on the same inverted index foundation. The core data structure is identical. The engineering trade-offs diverge entirely. Let's lock in the architecture. The entire Google search system is a 4-stage pipeline. Stage 1, Googlebot crawls 20 billion pages per day, prioritized by a URL frontier using domain authority and freshness signals. Stage 2, raw HTML lands in Bigtable on Colossus. MapReduce and Cloud Dataflow build the inverted index, with delta-encoded compressed posting lists for 2 to 3x space reduction. Stage 3, PageRank iterates across 130 trillion URL graph edges to compute authority scores. Stage 4, the query serving stack applies BERT-MUM intent classification, fans out to thousands of index shards in parallel, and merges ranked results in under 200 milliseconds. Every search engine from Bing to Elasticsearch runs a compressed version of this exact pipeline. Google's entire advantage over AltaVista came down to one data structure choice: the inverted index plus PageRank. Architecture decisions made in 1998 still serve 8.5 billion queries per day. Next video, how Elasticsearch shards inverted indexes across hundreds of nodes, and why shard count is the decision you can never undo. Subscribe so you don't miss it.